Explore more about the topics you love with Toppr. Subscribe now and keep learning.
Continuing our study of relations, let us look at what is a universal relation. Now, a universal relation is denoted by capital RU, which stands for universal relation, and it is defined on a given set. And here the set we have taken is set A. And so we can now define universal relation on set A as the set formed by containing all the ordered pairs that belong to the Cartesian product of A with itself. So, we will now understand this definition by means of an example. We know that if we have a set capital A consisting of elements A1 and A2, so we are taking a small set consisting of only these two elements, and suppose we want to find the Cartesian product of A with itself, then it will result in the following ordered pairs. We will first have A1 with itself as the first ordered pair, followed by A1 with A2. Next we will have A2 with A1, and finally we will have A2 with A2 as the final ordered pair. So here we have seen that when we had a set A consisting of two elements A1 and A2, the Cartesian product of that set with itself will consist of these ordered pairs. And now, universal relation on set A can be defined as a relation in which it consists of ordered pairs of the form A, B such that A belongs to the set A and small b also belongs to the set A. So now we can define a universal relation on a set A as consisting of all the ordered pairs that are there in the Cartesian product of set A with itself. So we can now write universal relation on this set A therefore consists of all these ordered pairs that are in the Cartesian product, and so we can now write A1, A1 as a element of this set, that is the universal relation. Likewise, we can also write A1, A2 because it is there in A cross A, and so it will be there in this set as well, or this relation as well. Now the next term is A2, A1, and that will be included as well, and finally the last element is the ordered pair A2, A2. So we now have this relation which consists of a set of all ordered pairs that are there in A cross A. So we have now defined a universal relation on a set A as consisting of all the ordered pairs that are there in the Cartesian product of A with itself. So we can now also note, or we can also represent this universal relation using the set builder form. And using the set builder form, we can now write universal relation on a set A is consisting of all ordered pairs of the form A, B, where A belongs to the set A and B also belongs to the set A. So we have now seen what is a universal relation. Let us now move on to the next type of relation known as a void relation, or also known as an empty relation. Well, continuing our study of relations, let us look at what we mean by a void relation, also known as an empty relation. Well, let us first look at the definition of a void or an empty relation. The definition says, a relation on a given set A is said to be empty or void if no element of that set A is related to any other element of that set A. Well, the definition says a relation on set A is void or empty if no element of set A is related to any element of set A. Now this is a little difficult to understand initially, but we will look at this with the help of an example. So suppose here we have an example wherein the set A is containing the elements 1, 2, 5 and 8. So we have fixed our set A as containing these four elements, and now we have defined a relation R such that it consists of all ordered pairs of the form A, B such that A is an element of A, that is small a is an element of set A and small b again is an element of set A. But there is yet another condition to this, and the condition here is A multiplied by B is equal to 7. So now in this relation capital R, we have to find all ordered pairs of the form A, B such that A into B is equal to 7. But if we look at this set A, then you will realize that if we select this first element or first coordinate as 1, then if we multiply it with any other coordinate, we will never get A into B is equal to 7. So in other words, regardless of whichever two numbers you take out of these four numbers, you will never get A into B as equal to 7. So we can now say that this relation therefore consists of not even a single ordered pair. So because this relation does not contain even one ordered pair, we say this relation R as an empty or void relation. And this empty relation is defined with respect to a set A. So To understand this example clearly, let us look at this in more detail. So I have a set A consisting of elements 1, 2, 5 and 8. And now the relation here has a condition that we need A into B should be equal to 7. Now if you fix our A as 1 and if you give any value to B, you will realize that for no value of A and B where A is equal to 1 and B is equal to any one of these values can we get a 7. So if we write 1 into 1, we will not get a 7. Likewise, if we write 1 into 2, we will again not get a 7, and continuing in this manner, you will combine any two elements of this set with itself. And so finally coming to 8 into 8, it will again not be equal to 7. So regardless of whichever two numbers you take out of these 4, you will realize that the product of no two numbers out of this 4 can be equal to 7. And so we say that this relation is not satisfied by any ordered pair of the set A cross A. And so because no ordered pair is contained in this relation R, we say that this relation R is an empty relation or a void relation. To see an example of another empty relation, let us now define a set B this time, and the set capital B can be said to consist of elements 0 and 1. So we've taken a set B consisting of these elements, and suppose if I have a relation R defined on the set B such that we are interested now in the ordered pairs of the form A comma B such that both A and B belong to the set capital B. So we now have both elements A and B belonging to the set capital B, but we also have another condition that represented by this and this here can also be replaced by an and, because this is one condition that has to be true, this is the other condition that has to be true, and the third condition here is, let us take a condition which says A plus B is equal to 3. So now we are looking at this relation R, which consists of all ordered pairs A comma B such that A and B are elements of set B, but we also have another relation that A plus B is equal to 3. And now we will have to select those numbers out of these which add up to give us a 3. Now if you form any combination of these two numbers, if you write 0 plus 1, it will not give us 3. If you write 1 plus 1, it will not give us 3. If you write 1 plus 0, again it will not be 3. And finally, combining 0 with itself also will not give us 3. And so we cannot find a single coordinate pair or a single ordered pair here such that their sum gives us a 3. And so R in this case will be a set consisting of no ordered pair. And so we say that because the relation R consists of not a single ordered pair, R is therefore an empty relation.
Explore more about the topics you love with Toppr. Subscribe now and keep learning.